Hello guys, and welcome back to my YouTube channel. Today I thought I would go over a little practice test that I made that covers drawing Newman projections, it covers resonance, chair diagrams, IUPAC naming, and I also touch a bit on stability and naming alkenes. So the first question says, consider the bond line structure and draw the Newman. So they gave you a Newman projection where you have to essentially fill in 3 of the boxes. What you have to do is figure out which carbon is in front. So let's label this carbon C1. And C1 we know is attached to an OH group. So on our bond line structure, what we need to do is find the OH group. So here I can see there's my OH group. Therefore, this must be carbon 1. And the front carbon in the Newman projection is also going to be the same carbon that you are staring at with either your eyeball or your human that you're going to draw in beside the bond line structure. So I always like to draw a human. If you need a refresher on why I draw a human, please go back to my Newman projections video. I go over this entire process. And since I just drew my human on the right-hand side of my bond line structure, I must draw in my dash and my wedge, which are my arms, where when I am standing on the right-hand side, my left hand is going to be on the wedge, and my right hand is going to be on the dash, where dashes line up with dashes and wedges line up with wedges. So all I have to do from here is go back to my Newman projection, pretending that I split our Newman projection in half, to a left-hand side and a right-hand side. Whatever matches with the left-hand side will also match with my left hand. So anything on a wedge. So the left hand, let's depict it in green. So all wedges I shall draw in green. So we see that on a wedge, so the atom on the left-hand side of the Newman projection in the front also is a hydrogen. Boom, we draw on a hydrogen. Now, we can say if you are on a wedge, you're going to be on the same side as the other wedge. So here, if I draw this hydrogen in pink, then this hydrogen will also be on the left-hand side in the back though. So it is connected to carbon number 2. Or once again, this is arbitrary labeling. We're just saying we're looking down this carbon-carbon bond axis, and that is what we are depicting in our Newman projection. Now we just need to fill in the top of our Newman projection. So let's pretend we have a sky where there's clouds, and we have the ground where there's grass. In our bond line structure, what is pointed up towards the sky on carbon number 1 will also be pointed up towards the sky in our Newman projection. Here we have an ethyl group pointed up towards the sky. And this group extends towards infinity and beyond. It will approach the sky. Therefore, we just put a CH2, CH3 group, which is an ethyl group attached to carbon number 1 going up towards the sky in our Newman projection. So we only have one more box to fill in, and that is the group that is going down towards the ground in the back of the Newman projection. So that would be attached to carbon number 2. So here we see that attached to carbon number 2 on a dash, which is going to be our right-hand side, is the CH3 group. Once again, if nothing is drawn in at the end of one of these wedges or dashes or even a line, you presume it to be a CH3. So if I draw in that CH3, or if I don't draw in that CH3, I am saying the same thing. So that CH3 is already drawn in for me. It is on the right-hand side of my Newman projection, because once again, it lines up with my right hand, which is on a dash. So it will also be on the same side as the other dash, which would be the OH group attached to carbon number 1. So now finally, the group going down towards the ground, attached to carbon number 2, is a chlorine group. So all I need to do is draw a chlorine group in the down position in the back of the Newman projection. And that is it. That would be my answer to this question. Now let's skip to the next question, where it asks us to provide the IUPAC name for the following structure. Once again, if you want to go back to my lecture on IUPAC naming, please check out my last video, because in this problem set, I am just going to be going over the answers to these questions. I'm going to be giving less of a lecture. So please go back to my IUPAC naming video if you have any questions, comments, or concerns. So step 1 is always to identify the parent chain. So this is going to be the longest unbreakable carbon chain. Here, I would go 1, 2, 3, 4, 5. So 5 corresponds to pent. So parent is going to be pent. So the second question that I must ask is, on my parent chain, are there all single bonds between the carbons? Or is there a double bond present? Or is there a triple bond present? Here I can see, starting at carbon number 3, there is a triple bond. If there's a triple bond, you must write YN. But since the triple bond does not start at carbon number 1, it starts at carbon number 3, you must depict this. So I must say 3 yin. And then the final thing you must do is depict the suffix of the top dog functional group. Here, the top dog functional group is the ester group. So the ester suffix is O8. So all that's left to do is on the side opposite to the parent chain, I need to draw in the name of that group out in front of the entire name for an ester. So here, there are 2 carbons. So we have an ethyl group out front. This would be how to name this structure. Question number 3. It says only carbons 1, 3, and 5 undergo nucleophilic attack. Why? Draw resonance hybrids, show your arrows. So what do we got to do? We got to draw resonance structures. But first, let's go over what a nucleophile is. So a nucleophile is going to be something that is negatively charged or delta minus. So it has electron density that it uses to go and attack something that it likes. Well, what do nucleophiles like? Based on opposites attract, negative charges like things that are delta plus or positively charged. So let's draw some resonance hybrids and see where the positive charges are. Draw my first resonance hybrid. Let's say starting at carbon number 1, I see a pi bond. I'm going to flick this bond 2 up because I want to see all the intermediate states. If I flick those 2 electrons 2 up, then carbon number 1 goes into an electron deficit because the 2 electrons initially in that pi bond pop up in pink onto that oxygen. The oxygen gains electrons, becomes negative, and carbon number 1 loses electrons, becomes cationic. So then we say, okay, this could be resonance hybrid number 1. This places a positive charge on carbon number 1. So a nucleophile could come in and go, bada bing, I like you, and attack it because opposites attract. But let's keep going. Let's draw another resonance hybrid. Let's say this went to in. What do we get? Carbon number 1 was initially in an electron deficit. When these 2 electrons moved over to in, carbon number 1 gained an electron and now becomes neutral. And carbon number 3 is left in an electron deficit. Lose electrons, become cationic. So now we see that carbon number 3 also, in one of the resonance hybrids, has a positive charge. So a nucleophile can come in and also attack carbon number 3 because opposites attract. So once again, we are just proving what they told us in the question. So now I need to draw one more resonance hybrid that shows me why carbon number 5 might be attacked by a nucleophile. So the last arrow I'm going to draw is these 2 pi electrons going to in, where the electrons move from in between 5 and 4 to in between 3 and 4, where carbon number 5 will become cationic and 3 will become neutral. So carbon number 3 gains that electron and carbon number 5 becomes cationic. So now we see why carbon number 5 also is subject to nucleophilic attack, because one of our resonance hybrids shows us that we have an electron deficit at carbon number 5. So this would be your answer. You would have to draw all 3 of these resonance hybrids and then just briefly state, well, nucleophiles will attack carbons or atoms that are in an electron deficit because opposites attract. So now for question number 4, it asks us which carbocation is more reactive and why. So we must remember that stability is inversely proportional to reactivity. So if you increase the stability, you're going to decrease the reactivity. And if you decrease the stability, you're going to increase the reactivity. So what makes something stable? Well, in organic chemistry, you usually argue stability via resonance or inductive forces. So stability is resonance or 2 induction. So question is now, can we draw a resonance hybrid for either of these structures? I can see for structure number 1, I can indeed draw a resonance hybrid. I can go 2 in, 2 up. Resonance. So I can delocalize those electrons. This is stabilizing. Therefore, this carbon does not have to bear that negative charge 100% of the time. It actually shares it. These electrons are spread via resonance. So this increases the stability and decreases the reactivity. Whereas in structure number 2, it cannot go 2 in, 2 out. Oh, I break a sigma bond. There is no resonance structures that we could draw. So since we cannot draw a resonance structure, we can then ask, okay, well, is there any induction? Well, yeah, I guess 2 atoms away, this carbonyl group is pulling electrons towards itself, aiding a little bit in stabilizing this negatively charged carbon, but this effect is not as strong as the physical movement of electrons, which is via resonance. So structure number 1 would be more stable. So structure number 2 is going to be more reactive because you cannot stabilize this negative charge via resonance, and the other structure can. All right, question number 5 says, draw the chair conformation for the following structure and perform a ring flip. Which chair is more stable and why? Once again, I have a video that's more of a lecture. In this question, I'm just going to be going over the answer. So here, step 1 is you always want to draw your right-handed chair. So following the same procedure that I went over in my previous video, I would draw in my right-handed chair. After I've done this, I want to label the atoms on my hexagon from 1 to 6 in the clockwise direction. So I usually start at the top. Once again, this is arbitrary. You can choose to start at whatever carbon that you want. I just prefer to start at the top carbon. 1, 2, 3, 4, 5, 6. Now, the next thing you must do is label the carbons on your chair, 1 to 6, also in the clockwise direction. What carbon you choose to label number 1 is arbitrary, but you must label in the clockwise direction if you've labeled your hexagon in the clockwise direction. So I'm going to start at the top right-hand corner. Once again, this is preference, and a lot of textbooks also choose to start labeling at the right-hand corner. 1, 2, 3, 4, 5, 6. So now, on atoms number 1 and atoms number 2, we are going to draw in substituents that are not hydrogen. So on atoms 3, 4, 5, and 6, I can just draw in hydrogens at the end of all of those bonds that I drew in. Because if I did not draw in a hydrogen at the end of all those bonds, it would be presumed that those would actually be CH3 groups. And that is not what my hexagon is showing me. So I must draw in those hydrogens. Now on carbon number 1, I have a wedge with a CH3 group. Therefore, on my dash must be a hydrogen. So now, wedge equals up, and dash equals down. So all I must do is find the up bond, and that is the bond on my chair that my CH3 group will go. So here I have an axial up bond. It extends to the sky. Therefore, my CH3 group will go on the axial up. Axial up. The hydrogen is on a dash going down, so therefore the hydrogen will be equatorial down. On carbon number 2, I have my T-butyl group going in the down position, so dash. So which bond is the down position? Here it would be the axial bond that is extending down towards the ground. So I would say T-butyl is axial down. Therefore, my hydrogen, which would be on the wedge, is going to be equatorial up. And once again, this is literally just because the CH3 was on a wedge. Wedge equals up, so you had to find the up position. On carbon number 1, the up position, the bond that extends towards the sky, is the axial position. And in carbon number 2, the hydrogen on the wedge, the up position was actually now the equatorial bond, because if you extend this bond to infinity and beyond, it is going up towards the sky, whereas the axial position on carbon number 2 goes down towards the ground. So now we have to perform a ring flip and then evaluate which chair is more stable. So to perform a ring flip, step 1 is to draw your left-handed chair. Once again, I go over this in my video on how to draw chair conformations, so please check it out. Now what I'm going to do is I'm going to relabel my carbons, except for I'm going to rotate the labeling over 1 in the clockwise direction. So carbon number 1 initially was the right-hand corner. I'm going to move it down 1. So carbon 1 will now be here, and then I will label clockwise around the ring. 1, 2, 3, 4, 5, 6. So now, on carbons number 1 and carbons number 2, I'm going to draw in the bonds in the same fashion that I would have for my right-hand chair. So you have an axial down, an equatorial up. You have an axial up and an equatorial down on carbon number 2. So listen to me very carefully. Down stays down, up stays up. Equatorial bonds switch to axial, and axial bonds switch to equatorial. So on carbon number 1, the CH3 group is in the up position on the right-handed chair. So in my left-handed chair, I need to find the up position. So the up position is going to be the equatorial bond. Therefore, my CH3 group on carbon number 1 in the left-hand chair would be on the equatorial up position, because up stays up and axial switches to equatorial. My hydrogen has to stay in the down position. Here, the down position is the axial bond, axial down. Then on carbon number 2, the T-butyl group must stay down. So the down bond would be the equatorial. And the up bond would be the axial up, and the hydrogen would go on the up position because you want up to stay up, down to stay down. So if I label these, here I would have an equatorial up. Here I would have an axial down. Here I would have an axial up and an equatorial down. Starting at the CH3, axial flips to equatorial, but up stays up. Then moving to the hydrogen, equatorial flips to axial, but down stays down. For the hydrogen on carbon number 2, equatorial flips to axial, but up stays up. For the T-butyl group, axial flips to equatorial, but down stays down. And there you have it. That would be your left-handed chair. I decided to not draw in the bonds on carbons number 3, 4, 5, and 6 just for simplicity, because all we really care about is what happens to those groups that are non-hydrogen. And here we see, when we're trying to say which chair is more stable, well, which chair has the bigger groups in the equatorial positions? The equatorial positions create more space. It decreases the steric hindrance. So in our left-handed chair, we could see that our T-butyl group is now in the equatorial position, and our CH3 group is also in the equatorial position. This is different than in our right-handed chair. They were both in the axial positions. So right now, the way we have depicted this, the left-handed chair would be the more stable chair conformation. So now finally, I actually have not done a video on this, so I will briefly go over it. Classify the following alkene as E or Z. Step 1, you want to pretend that you're going to split this double bond in half. Chop. And I mean from, let's arbitrarily label this double bond, carbon 1 to carbon 2. Chop in between carbon number 1 and carbon number 2, right in half. So now I want to compare the groups on the left-hand side of the chop and on the right-hand side of the chop. And I'm going to compare them atom by atom based on their atomic number. So here, attached to carbon number 1, I have a carbon versus a chlorine. So the chlorine group will win. So now I must go to carbon number 2. Here I have a hydrogen versus a bromine. The bromine does. So now, based off the two groups that won, you ask, are they on the same side or are they on opposite sides? Here you can see those two groups are opposite to one another. And opposite corresponds to E, whereas Z corresponds to they are on the same side. The way I always remembered this and how my professor showed me was they are on the same side, like they are on the same side, is equal to Z. So how this would look if it was Z, I shall show you. And the bromine there. and you went through the same procedure of chopping the double bond in half, and then figuring out which group wins on each side, here the chlorine would win on the left-hand side, and the bromine would win on the right-hand side. Therefore, now these are on the same side, so this would be Z. So structure number 1, this is E, and structure number 2, this would be Z. Is Z. That is it. That is all. All right, guys, that is it for our practice test. We went over stability, we went over Newman projection, we also went over how to draw chair diagrams and perform a ring flip, and we did a little bit of classifying alkenes as E or Z. Hope this video helped, and let me know if you have any questions. Have a great night. Bye.